my clock. Thank you very much for this nice introduction. I'm very happy to be here today with you, at least online, to share a bit of the work we've been doing in recent years, particularly with a focus on hydrologic extremes, and I'll pick the topic of floods here because it's most suitable. So we have a research group, and in this research group a few years ago we started to decide that we wanted to look at things that are big and that we can exploit. Big models, big data, and big literature. And these are the three things that I want to give examples for. So I'll organize it in that way, and in all three cases I'll pick examples of our work that deal with flooding, though we have other work on other extremes like droughts and landslides. So if you've been following the recent analyses of climate impacts, then you've seen that our climate seems to be more sensitive than we had expected. And I'm sure Haley Fowler will say a lot more about that when she gives her presentation. But it seems like our climate is more volatile than we had anticipated. And there was just a recent new projections from the German Weather Service, and they were all above all the projections from the IPCC. So we're expecting things to get a lot worse, and this will hit our areas. This is a region in Germany shown here on this picture that was hit 5 years ago very badly by extreme rainfall that had never been experienced by the people living there, at least in their lifetime, and caused a lot of damage. So let me say a few words and use this example to give you an idea of what the problem is. So extreme events challenge us with their severity and impact, and increasingly the risk we experience is different from the risks we expect. And if we look at this particular area here in Germany, so this is in the picture, it's the same area that was on the picture before. We of course have, like everywhere, like the UK and in other places, we have an anticipation of what kind of flooding we expect in the form of hazard maps. So you see them here. So the dark blue line is the river. The light blue is the anticipated 200-year floodplain. And this is normally derived from a mixture of analyses, but particular the kind of historical observations that we have, which are here shown as annual maximum floods for this particular area. Now, this timeline goes about up to 2020, and it starts, like so many time series that we have, in the 40s and 50s. So most of our instrumental records with direct measurements are about 80 years, 70, 80 years long. Now what happened in 2021 was the flood event that happened looked like this. So the red bar on the right you see is dramatically higher than anything experienced in the instrumental record. And the flooding that occurred, you see in the middle in the graphic of in this map, is vastly bigger and wider than what was anticipated by the previous estimates of the return period. And the flooding that you see in the picture was devastating. The problem was so vast that there were over 200 fatalities, not just in this small area, but along the larger region. And the biggest problem, I think, from our perspective, from developing this kind of hazard maps, is that almost 60% of the people who died in areas where they assumed to be safe. So they died in areas that, according to the hazard maps, should have been safe, and some people actually evacuated to these areas where they then died due to drowning. And Given that the extremes are likely to become more and more different from the historical, we will experience more and more problems because our experience is an increasingly poor guide for what we expect and how we behave during extreme events. So this is a commentary we published just recently where we debated that if you look at a decrease in fatalities over the last couple of decades or so, then this decrease came largely from improved monitoring, some improved modeling capabilities, but in a lot of areas, including flooding, this reduction in fatalities has stalled and might even have gone up. We don't have enough data yet to say that, but there's certainly not an increasing, a further decrease in flood fatalities. And what we need to understand is going forward, what methods, what approaches can we use to further reduce this and to avoid fatalities going up again, because extremes and hazards will go up. And part of that is, as part of these early warning systems, is disaster risk knowledge, is providing people with the information they need to know what they should anticipate, and then also explaining them how they should behave when something like this happens. So what is the typical modeling chain that we use to make these kind of estimates? Well, for future periods, they might be this kind of top-down modeling chain. So we have emission scenarios. These are used to drive global climate models. These are then used to create meteorological projections by downscaling global climate model estimates or by using numerical weather prediction. These are used to drive hydrologic model to decide how much runoff will be produced from the extreme rainfall. And we might link this to return periods, flood frequency analysis to have an idea on what expectation we can have every year for a particular flood level to occur. These are then used to put through a flood inundation model, so we actually know what areas will be inundated and what the impact will be of this flood event. Now, the problem is that all of these steps are very uncertain, and that this kind of framework increasingly provides us with poor estimates of what will actually happen. So let me start by big flood models and talk about that as first example. So this first example, or the first two examples, actually are from the PhD of Laura de Witt, which she did together with colleagues from University of Bristol, Geoffrey Neal and Gemma Coxon, on the topic of flooding. In her first study, she was attempting to quantify the uncertainty in large-scale hazard models. So in large-scale hydrologic models that predict the 100-year return flood. What she did was she compared 6 different approaches, so 4 different hydrologic models, on the top right, and at the bottom 2 statistical strategies, so regionalized flood frequency analyses. And these models are run here for historical data in the typical top-down framework that I was just showing. And because we here ran the model against historical data, we also have historical observations of the 100-year flood that we can compare the model against. And what is shown in these different maps are biases in terms of model prediction versus actual observations. Red means the model underpredicts, blue means the model overpredicts. So that's the bias here. And the problematic thing we see is that these 6 maps for 4 different models and 2 different statistical strategies are all significantly different. So that means all the models give very different estimates, and particularly they make very different mistakes across the US in this case. So if we look at this and we try to understand whether there's any kind of pattern or structure in these biases, then we see on the left here, when we plot the bias, positive in blue and negative in red versus basin elevation, then we see that the Fathom RFFA, so one of the statistical approaches, shows that if we have higher basin elevation, we have a more negative bias, whereas Kammer flood model shows the opposite. We have a more positive bias if we go to higher areas. If we look at the standard deviation of basin elevation, so how variable is the topography, then we find that PCR globe shows an increase, so more positive bias when we have more variability in topography, whereas the height model shows essentially a flat line, so there's no difference. So that means all these models have different kinds of errors and different kinds of uncertainties, and they also regionalize in different ways and with different variables. And that's a big problem, because if you want to anticipate what happens, then how do we bring all of this together and have a meaningful estimate? So this kind of top-down approach where we propagate things at the moment, at least over large areas, leaves us with very large uncertainties. So what else can we do? And that's where we come to big flood data. And here big flood data means we have a lot of data that either comes from observations or that comes from models. But they're big because they cover global estimates. So they show large variability because they cover very large areas across the world. So this was a second paper with Laura, by Laura, where we looked at flood hazard potential to understand global floodplain settlement patterns, and I will explain that in a moment. So if we find that this top-down approach to propagating from projections or observations to impact is very uncertain, then is there an alternative approach that we can use? And one of these alternative approaches that we looked at is, can we stress test the global river network to understand where an increase in flooding would be most problematic and where it might not be particularly problematic, so that even if the uncertainty is large about what might happen in the future, we can still at least anticipate whether that future is a problem or not. So we can identify regions that are problematic. So what we do is we essentially ignore the first part of this top-down modeling chain, and we only focus on the end, so the flood frequency analysis. So what we want is we want increasingly larger flood magnitudes that we assess. We assess them using a flood inundation model, so we can understand at least the potential impact these flood volumes might have in a particular region. Now, if we do that, we can actually use the information coming out of the model in a clever way to give us, if you like, a sensitivity index that tells us whether each location that we study is very quickly becoming problematic if floods increase, or only later, or maybe something in between. So if we take a flood inundation model and we look at a river reach, so a stretch of river, maybe 500 meters, and we now run different models with different return periods, different estimates with different return periods, meaning, so on the left you might have the annual flood to 50-year flood, the 100-year flood, all the way to maybe the 500-year flood, so something very extreme. That means we, from left to right, we have more and bigger flood magnitudes. If we run them through a flood inundation model, then we can estimate the flood extent that is produced by each of these flood volumes. And Interestingly, the patterns we get are generally relatively simple. In some places they might follow the red line. So that means if the return period increases, if the flood volume increases, we very quickly have an increase in flood extent. So flood extent grows very quickly. Or we have the blue line, and that means if the flood volume increases, the flood extent does not increase very quickly, but only when we go to very, very high volumes. Or we have something in between, which is somewhere in the gray area. And because these patterns are relatively simple, we can use a very simple polynomial equation and can say that the flood extent equals the return period to some power b. And we can fit this equation by estimating parameter b and use the value of b as an index of what the location is like. Yeah, so if that index b is smaller than 1, it means the river reach follows the red line and the area is sensitive to low magnitude floods. If it is larger than 1, then it means it follows the blue line and it's sensitive to rare extreme magnitude floods. If it is about 1, then it's somewhere in that gray area. We only used equations that show a fit to the data, that it's better with has an R square more than 0.9, so it has a very good fit. Now, to apply this kind of sensitivity index, we estimated for existing global model runs. So all the runs are already there, the data set is there at 90-meter resolution, and with a return periods from 5-year return periods to 1,000-year return periods. So from very common floods to very, very rare floods for each location. Now if we do this, and we do this for over 1 million river reaches, 500-meter stretches across the world, then we get a pattern that looks like this. So the red color again sensitive to small floods, the blue color sensitive to large floods. And we see these kind of patterns in different parts. So we see that large parts of China are sensitive to large floods, but insensitive to small floods, whereas in Europe it's more red, so it's the opposite, and so forth. So we see that different parts of the world organize differently. What organizes these patterns is then the question, and we find that if we plot these 1 million points from top of the catchment to bottom of the catchment, so where this river reach is, versus upstream drainage area, then we see that we have in the top of the catchment a sensitivity to large floods. In the middle we have equal sensitivity and sensitivity to small floods, and then at the bottom we again have sensitivity to large floods. So if we organize that, we see that it's the type of topography that we expect in these different parts of the catchment that organize this. So at the top we have confined rivers, streams, so high slope next to river channels, steep bedrock streams. That means we need, in order for significant flooding to occur, quite a large volume. In the middle we have partially confined, so these are the transition areas from steep mountainous to flat sedimentary basins, and we call them partially confined. And then at the bottom we have these laterally unconfined areas, which are the large floodplains. So with these, we have an estimate or an organization of the sensitivity to flooding, to flood inundation, to inundated area. Now we can do the same thing. So now return period not against flood extent, but against people exposed. So who is actually exposed to the flooding, because even if a flooded area might be relatively large, if people don't live there, then it might not be particularly problematic. So we repeat the same exercise, but now it's not flood extent, but it's people exposed that are equal to return period to the power of b in the same way as we did before. And then we can repeat the analysis and we can look at what the result actually tells us. And so here we present the result on a bit more aggregated level, so by small units, administrative units, and by different parts of the world. So the colors show population on the floodplain in percent. So the darker the color, the more people live on the actual floodplain, whereas it's lighter, then it's less. And then these pie charts are organizing the rivers in river reaches in this particular domain. So for example, for sub-Saharan Africa, as portion of reaches and population exposed on reaches in these three kind of categories: confined upstream rivers, partially confined transitional rivers, and laterally unconfined deltas, and to see what is the proportion. We see immediately that the partially confined cover a very large fraction, even though we have areas where other parts, like here, laterally unconfined, are also very large. The overall result that we find that that in many areas disproportionately more people live on downstream floodplains for different reasons. So reasons might be that these are areas where there's large agricultural regions, so where people actually can support themselves, or because large cities are in the coastal areas. So that might be other reasons. Now, if we bring these two aspects together, then we get this kind of pattern. So we get an idea of how global settlement patterns relate to sensitivity to flood extent and sensitivity population exposure. So might take a moment to think about this figure. So on the horizontal axis, we have flood extent sensitivity with the value of 1 here. That means if it's left of 1, then these are areas sensitive to frequent low magnitude events, and right of 1 are sensitive to rare extreme magnitude events. And the same on the vertical axis, population exposure sensitivity, value of 1 here, above sensitive to rare extremes, below sensitive to frequent extremes. And what we quickly see is there are two different clusters. So there are parts of the world where floodplains are very sensitive to frequent low floods. But we also see that in these areas, so sensitive to frequent low floods means it's a value below 1 on the horizontal axis, but it's a value around 1 for exposure, for people exposure. That means people live everywhere in these floodplains, even though they should flood regularly. But what it means is that people have adapted to the risk. So Europe is part of this largely, and people have simply built levees that protect them. So there is this kind of adaptation that is possible. Now this upper part are floodplains that are most sensitive to rare floods, so they're towards the right of this plot. And here, interestingly, the population is also towards the top, so people live quite far away from the rivers. And that might be because they use the floodplains for agriculture, for example. So here, particularly for these regions, we have significant danger from increasing flood magnitudes given climate change, because eventually these areas will flood if the flood that arrives is simply large enough. That means these areas will be in danger from flooding these people likely have never experienced, and that means there we have a huge potential to tackle future risk. With the plot on the circle on the left, people have adapted to the risk. but people have adapted to the past risk. So if their future flooding or future flood extremes are much more extreme, then what we might find is that we have a risk of levees being insufficient and other protective structure being insufficient. So those two examples have shown us how we can use and have to understand variability in models and variability in large data sets that we can exploit, that we can understand, to at least understand the variability in risk that people are exposed to. Now, the third example I want to give is how we can use big flood literature. And this is based on work from one of my postdocs, or former postdocs, Lina Stein, who just left to take up a faculty position. And we published this paper last year called Wealth Over Woe, Global Biases in Hydrohazard Research, which was a very large analysis of literature together with IBM research. So why do we care about this? Well, if you're a PhD student or a student who has to do literature reviews, you might have it might have occurred to you already that the literature is growing dramatically, and that's a real problem for us. So here's an example from the IPCC. On the vertical axis is number of publications, and in the different colors, the bars show for each report from the IPCC, or for each assessment period, how many papers were used and were looked at to support each report. And this up here is 30,000, and you see that in time, vastly more papers for each report have been used and have been looked at to get an idea of what's going on in the world. But even though the increase is exponential practically from in terms of the number of papers that were evaluated, we see here on the right now the fraction of papers that were used. So 100% would be all the papers that are available and relevant to the topic. And this is the fraction, and we see that while we have a huge increase in papers considered, we have also at the same time a dramatic decrease in the number of paper, or the share of papers that could have been used. So the AR5 has only just over 20%, so 25% or so, whereas the initial report had over 60% of the publications. And this kind of pattern is exactly the same when we look at hydrology, my area, or if you will look at hydraulics or natural hazards or other areas. So here's a plot where we show the increase in the number of articles published per year for the main hydrology journals. And so if you were doing your PhD in the 70s, or you were studying in the 70s, then you had only to read Water Resource Research and Journal of Hydrology because the other journals weren't there. But if we go further along, then you see that more and more journals get added, and that also the journals that are there tend to publish more papers. And so about 2000, 2002 is when I did my PhD, so it was already in the order of 1,000 papers a year. Now, if you're in recent years, 2020, you see that the number of papers in the last 5 years or so has practically exploded, which is partially due to MDPI journals like Water that have been added to the mix, but also other journals like WR and others publish a lot more papers. That means now we're in several thousand papers a year. So this is 5 years ago. So it was already 8,000 and it has gone up since. That means we have a huge potential in the literature to learn something because we have so many studies, but it becomes impossible to look at these studies manually and to read all these papers. doesn't matter how motivated you are, it's just practically not possible. So what else can we do? Well, we can talk to people like IBM Research that help us with using better tools to digest the information that is in these papers and extract it in a way that it becomes meaningful to us. So that's what we did. So here's basically the steps we went through. We started with a database, a semantic scholar of about 100 million abstracts of published papers. In the first step, we used deep search, an algorithm from IBM Research, to ingest analyze the data. So it uses natural language processing to be able to ingest unstructured data like text, and it enriches it with metadata, so we can filter out abstracts that are not in English or extract other information from it. We then filtered it with hydrohazard specific terms. So that means we created a catalog of terms that we were looking for to identify those abstracts that actually dealt with hazards. So here's an example. So this is the example for landslides, not floods, but it's the kind of research and query that you might use for Web of Science, or so when you look for things. Landslide or mudslide or rock slide with a star to include the plural and so forth. And that reduced 100 million papers to about 600,000 papers that were relevant, that had natural hazard content. And then in the next step, what we then did is we know we have a long list of abstracts and we know that they deal with hazards, but where do they deal with hazards? So what location do they study? And we used this next step by essentially geocoding using trying to extract from each abstract any kind of information that might tell us about where it is. So it might have, like shown here, information about a city or information about the country or something else, or it might be a river name. And then in the last step, we used Nominatim, so geocoding software and data from Natural Earth dataset to geolocate the coordinates that we have. So that actually uses largely OpenStreetMap. And that step again is not so straightforward, because if it might say Paris as the location of the study, but there isn't just one Paris. There's a Paris in France, there's a Paris in Texas, there are other places that are called Paris. So which one is it about? So then you have to combine different kinds of information. If it might also say Europe, then clearly it's Paris in France. If it might say the US, it might be Paris in Texas. So this kind of process is actually quite involved and has lots of potential for problems. And we used many iterations to figure out how we do this. Now, the result is then that we can now geographically allocate all the studies that we found. And we can understand where we do a lot of research on flooding, where we do little research on flooding, and so forth. So what you see here is that there are hotspot areas with a lot of flood research are Europe, so that was the most intense region here with this inlet shown here in a bit more detail, and the US, particularly the coastal areas, and then kind of areas in the South, Texas, so the areas hit by hurricanes, and then Asia, so there's lots of research in China in particular. And with that, we can take, starting from 100 million abstracts, we can understand what is the density of research, of active research, at least published research, that is present in different parts of the world. And we can also see where is there a gap of research. Now, if we analyze these results, then we can, for example, try to understand whether the research activity is proportional to the impact of floods in different parts of the world. So what we did here is we took all the regions of the world, the different countries in this case, and we grouped them by income group. So darker areas are high income groups, light low income groups. And if we then for the different income groups plot the number of people affected per country by floods versus the cumulative weight, so the weighting that we just derived from the number of papers produced in this area, then what we see is that we see a significantly earlier increase in the number of papers for people affected for high-income countries. So if we have floods that are affecting the order of 100 people, we see that these dramatically go up. Whereas we really have a factor 100 to go to, or less, to get to the same level of activity if we go to low-income countries, for example. So that's why our conclusion was wealth over woe, wealth over impact and negative impact from hazards. Wealth, not impact, is areas where there's a lot of money. There's very quickly responsive increased activity of research after disasters, whereas in other countries, low-income countries in particular, where the impact might be dramatically higher, the consequences for research activity are much lower. Now, if we overlay the two, if we now try to understand how well do research activity and impact match, then we see for flooding this kind of pattern. So what is shown here on the left is explained down here in the bottom left with this small graph, and that is research activity. If research activity is low, then it's this full color. If it's high, then it's this somewhat lighter color. If impact is low, so if few people are affected by flooding, then it's blue. If the impact is high and many people are affected, then it's reddish color. And what we try to balance is, where do we have low? So if you're on the blue side, impact is low, then it's interesting to see that despite low impact, the research activities can be very high. So we see this in Australia, parts of Europe, in parts of the US. So that might be because data sets are particularly favorable, or for other reasons. The problematic part is if we have the dark red, so if the impact is very high, if lots of people are affected by flooding, but if the research activity is low. And we see this particularly in parts of South America, large parts of Africa, and in some of these border regions between large countries in Asia. So these are areas where there is way less activity proportional to the impact that people experience in these areas. Now, what of course is the interesting question going forward is, where will future flooding be problematic, and do we have research activity there? Do we have experience, because the experience is captured in papers? And so if we look at this example, Global Flood Database, expectations as published in BBC of future flooding increase in the future, North America, or the red parts are the parts where we expect or have already observed more flooding. And you see that, for example, parts of Africa are red in both, parts of South America are red in both. That means we have areas where we expect future flooding. to occur and become much worse, but with low research activity. The thing with the research activity is not just a question of can we understand the flooding from a natural sciences point of view, from an engineering point of view, but also can we understand the socioeconomic system. So while we might have areas in other parts of the world which we can transfer in terms of the physical setting, so we might have other places that are dry or wet or particularly warm that we can, where we have studied and learned about flood processes that we can transfer to similar regions, even if there has been little research. But it gets a lot more complicated if we also have to transfer the impact side, the governance side, the socioeconomic and cultural aspects, because these are much harder to transfer. So we cannot use data or things we've learned in the US and say we apply these now in somewhere in Africa, because the sociocultural context is very, very different, and the governance structure is very different. So that makes it very complicated unless we have data really in specific regions, or at least very comparable. So in conclusion, I wanted to give 3 examples to show that we have to understand global variability of hydrologic systems with respect to floods and other extremes. But the variability that we have in space also provides an opportunity, because it means we have already large data sets modeled or observed that we can exploit. The 3 bullet points, so we must better understand model behavior. So particular, what we need to understand is how uncertainty and model quality varies across different locations. We can better exploit the tremendous variability reflected in both modeled and observed data to understand this partially. The nice thing here is that even, let's say, one global model run, even for a single scenario, has already so much variability because the model is not is spatially distributed. All the models we use at a global scale are spatially distributed. That means they do look at how rainfall, for example, relates to flooding from many, many places that we can study. So it's a huge data set produced by these different models. And thirdly, I think one thing that we'll have to do much, much better, and where there will be a lot of research in the next few years, is to take literature and to extract from the literature the data that we can actually use for our analysis. We have to do this using machine learning tools, text mining and other strategies, large language models, because it's impossible to do this manually, and increasing number of people work on this because there is a tremendous data source there if we know how to tackle it. And to close off, so my postdoc Lina Stein made this picture using ChatGPT, where she's representing her work, where she's sitting in terms of flooding from both literature and flooding from the kind of flooding that we experience and that we use and that we study. So thank you very much for your attention, and I'm happy to answer any questions that you